Hi everyone, let's make a start. Welcome to London Machine Learning Meetup. I'm Martin Goodson from Evolution AI, sponsors of the meetup. And today we're hosting Thomas Kipf, who is going to be talking to us about graph neural networks for about 40 minutes as usual. We will leave the QA till the end. If you've come to the meetup before, you're going to be bored of me saying this, but if you can put your questions into the QA function, not the chat, but the QA function, then when we come to the QA, we are going to be, the QA session itself will be moderated by Johannes Klitzperer from the Technical University of Munich. All you need to do is put your question into the QA, put your hand up if you want to ask your question yourself, and then I or Alessio, who's also a colleague from Evolution AI, will unmute you and you'll be able to ask your question yourself. If you don't want to do that, just don't put your hand up and we will ask, or Johannes will ask your question directly from the QA. I think that's all we need to say, so I'm going to hand over straight away to Thomas. Thanks, Thomas.
Thank you, Martin, for the nice introduction. I'm super excited to be here today and to be talking to you about relational structure discovery. As you've heard from Martin, my name is Thomas. I am currently a research scientist at the brain team at Google Research in Amsterdam. And I've already been talking here at the London ML meetup something like 3 years ago, and basically in the early days of graph neural networks. And I'm excited to talk to you today about one topic I'm particularly excited about, which is essentially extending the realm of graph neural networks to data domains where you're not necessarily given your data in the form of a graph, but maybe you only have nodes and you want to discover relations or edges, or you're even given perceptual data and you want to discover what the nodes are in the first place. And so today's talk, today's talk will be about relational structure discovery. And relational structure, what I mean by that is essentially representing the world's information in terms of entities and their relationships. And so entities and relationships are a very powerful abstraction. In a way, for us humans, it's very easy to interpret, like we understand the world in terms of objects, their relationships. It's the fundament on which we use language. And we can very easily interpret data that is given to us in the form of a graph. And at the same time, this form of abstraction is near universally applicable. So entities and relationships can be pretty much anything. For example, you could have entities represent atoms in a physical system. They could be users in a social network, or even intersections in like a traffic network or in a map. And similarly, relationships can be freely interchanged, and they can be pretty much anything in those data sets. And so what this abstraction allows you is essentially a near infinite kind of way in which you can combine information in a sensible way. And for example, you could exchange entities and relationships, or you could add new entities to a graph, and you would still end up with a sensible kind of representation. And so it doesn't come to a surprise that graphs, even though that graphs are essentially so widely and universally used in practice. And so in like modern technology, you have social networks, citation networks, maps and road networks, where you can, for example, represent intersections as nodes, and links or edges between these nodes represent road segments. And similarly, you can have communication networks, a worldwide web, energy networks, and so forth. But also things like knowledge graphs, where you have more rich information on the edges, like you have typed edges and directional edges that tell you about relationships between entities. It's a very useful and compact way of storing knowledge about the world. And similarly, you can also represent dynamical physical systems of the same type of abstraction. So nodes in this case would usually be atoms or for example, in molecular dynamics simulations, but also in classical physical systems. And you could represent relations as pairwise forces between particles, for example. And this goes on to biological networks like protein interaction networks and so forth. And so graph neural networks in the past 5 years or so have really become like the established method for learning with graphs. And so we've seen graph neural networks be applied for compositional reasoning tasks, simple tasks like node, edge, or graph classification. But also, as I mentioned earlier, for things like physics modeling, where you would, for example, want to predict the future state of a dynamical system, like the future state of each particle in a dynamical system, or forces or relationships between particles, and so forth. And we have seen a massive explosion of graph neural networks in the past 5 years or so, from like a community that started out with only a handful of papers a year to one of the fastest growing areas in machine learning, with up to thousands of papers coming out each year at this time. And one thing I want to mention is that the typical assumption we make when applying graph neural networks, or when thinking about graph representation learning, is that we know what the entities and the relations are. So essentially, we are given a data set in the form of a graph, and then we can apply these methods, and we can pretty much expect to get reasonable performance on all of these tasks. What I want to focus on in this talk, however, is what happens if we have incomplete knowledge about, for example, relationships. And this leads to problems such as link prediction or graph completion, where you might be given an incomplete graph or a graph at a particular snapshot in time, and you want to predict missing edges or missing links, or the future state of the system in terms of new relationships. And similarly, you can even take this to the extreme and say you don't know anything about the relationships, and you're only given some description about entities in your system, and you want to infer relations between them from scratch. And this, in this context, I'm going to talk about a model called Neural Relational Inference, and the wider problem of inferring interactions in dynamical systems. And the really interesting question that comes up is, what if you don't even have the nodes or entities? Like, we know that with graph neural networks, we get, with graph neural networks and related methods, we get strong generalization performance just because of these compositional properties of the data representation. But how can we make use of these if we, for example, want to apply these methods to perceptual data, where we're not given any information about nodes or entities? And this leads to problems such as such as object or entity discovery, where we'd like to discover the entities or objects that act as nodes in your representation from raw perceptual data, like from images or videos. And essentially, this corresponds to finding a grouping or a clustering of lower level features, so that the clusters, they correspond to the right abstractions that you can then use as input to your graph neural network. So the talk outline for today is going to be first about the relational aspect in relational structure discovery, and I'm going to talk about GNN-based link prediction and neural relational inference. And I'm going to talk about afterwards one particular model called slot attention for attentive grouping of low-level representations into abstract entities. And before I conclude, I want to briefly mention on how this can all be combined in a bigger picture model, where you essentially jointly infer objects and relations from raw perceptual data and use it to predict future states of the system, or to make or to reason about perceptual inputs. So before I dive into the main part of my talk, I want to give a brief introduction and background to graph neural networks. I'm sure many of you by now are familiar with the concept of a graph neural network, but essentially the bigger picture here is to have a model that at each iteration in the model, or at each layer, so to say, in the model, passes messages along the edges of a graph, agglomerates these messages, and transform them for each node in the graph. And effectively, all these models, they differ based on how you parameterize, or how you define these message passing functions, and how you define the agglomeration functions, and how you define like node update functions. And for our purposes here, graph is just a tuple as a set of nodes and a set of edges. And node features I will typically describe as vector hi, and edge features as a vector hij. And the predominant formulation these days for graph neural networks is the neural message passing formulation. And in a way, you can think of it as a model that passes messages along the graph, across the edges of a graph for multiple iterations. And at every iteration, you first compute this edge update here, which could be any kind of parameterized function that takes as input the features of your neighboring nodes, such as hi and hj here, and potentially also some additional features that live on the edge that are provided to you as an input, for example, xij in this case. And typically, this edge update function would be something like a small neural network, like an MLP, that acts on the concatenation of these vectors. And then by this simple edge update function, you get a message, which would be the new edge embedding. And later, you can then compute a node update function by essentially aggregating node features using some simple aggregation function like a sum, and concatenating the resulting aggregated features with separate node features you might have for your particular node that you calculate the update for. And again, this node function is typically parameterized as a simple small neural network. And the important part here is that all these edge and node update functions are shared across all locations in the graph. So you can immediately apply this to different graphs, to like if your graph changes in size, you can apply the same model, and you don't have to retrain the model typically unless there's some drastic distribution changes. Now, the main formulation, this neural message passing formulation, includes a couple of different definitions that you might also be familiar with. For example, convolution-based graph neural networks, which have been around for longer, are included in this definition in that they essentially only have a simple node update function, and the edge update function is simply a linear matrix multiplication with a weight matrix. And so here you would have a message function from the neighbors with w1hj, in this case, that transforms all your neighboring features in the same way. And you would have some kind of normalization constant here, alpha ij, that you can either pre-compute for the whole graph, or you could also learn it based on some properties of your graph. And in general, you could also have a separate update for the node itself, like a skip connection in this case here. Now, this extension, this formulation can also be easily extended towards relational GCNs, in which case you would now also have a different message passing weight update function for each relationship in the graph. Like if you have a graph that has multiple relation types, like a knowledge graph, where you have different edge types that describe the different relations between entities, then in this case, you would calculate you would assign a different weight matrix for each of these different edge types. And this simple model is enough to learn powerful representations of knowledge graphs and typically of relational graphs where you would want to, for example, do entity classification or link prediction. And one interesting connection to mention here is also the connection to multi-head self-attention, like the core update in transformer models, which are very popular these days across many disciplines in machine learning, like in NLP or in vision. And the main idea here is to essentially also learn the normalization constant for each aggregation function. So here, in the typical multi-head dot product attention formalism, you would have a bilinear product between your two neighboring features, and you would pass them through a softmax normalization. And that gives you essentially your edge weight in the graph. Now, having covered like the core graph neural network flavors, and of course, there's many variants of these, and many different extensions depending on the kind of symmetries your problem has. Like in this case, the models I presented in the last slide are all symmetric under permutation of the nodes in your graph, which is like one of these core symmetries you would want to take account for. But you could, of course, also include other symmetries in your model, for example, being equivariant under rotations, or shifts in terms of translations in your system. Now, one interesting aspect is how to use these graph neural network encoders now for link prediction. And the recipe is here pretty simple. You would simply apply the graph neural network encoder on the incomplete graph that someone gives you as part of your data set. And you would want to predict any missing relations or any future relationships coming up at a future time step in your network, for example. In this case, you would run the GNN encoder, which could be a number of layers of these message passing operations, either with shared weights or with separate weights per iteration. And then at the final step, you get a node embedding for each node in your graph. And you can simply perform link prediction by taking a simple decoder or scoring function that takes a pair of node embeddings and produces the probability of whether these two nodes should be connected or not. And that simple recipe, together with a simple contrastive loss, for example, where you would train this model by maximizing the probability of all the edges that you observe, and you minimize the probability of several negative samples that you choose of nodes that are not connected in your graph. And you would use negative sampling here because usually you have way too many negative edges in your graph, and it would be too expensive to compute it for all of them. Now, having covered essentially how we can perform link prediction in graph neural networks when you're given an incomplete graph, the more interesting question is, what can you do if you're only given nodes and you want to infer relationships from scratch? And this is, for example, the case if you have some kind of dynamic system where you, for example, observe different particles and their dynamics, and you would like to infer how these particles interact or what kind of forces they exert on each other. And this is important for analyzing dynamic systems in general, interacting systems, because you would want to maybe understand which kind of elements of your dynamic systems, for example, influence other nodes in your system. And in that way, if you can infer this interaction graph, this is useful for a number of downstream applications or for interpretability. And the way this model here works is that at each training iteration, you get one observation of your dynamic system. And this observation is usually in the form of a set of node features, where each node feature captures the trajectory of one single particle in your system. And so this could be, for example, a simple system where particles are connected by simple forces, like they're connected by invisible springs, and you would like to predict the forward dynamics of the system under these interactions. And the way we can simply encode the state of the system here is to apply a graph neural network on the observed dynamic system. Now, the interesting part here is that we do not have any knowledge about the interaction graph at this point. So what one would do is you can either pass messages on the fully connected graph, or if this is too expensive, you can make certain assumptions about the sparsity of the graph. For example, you could say, because nodes that are, or particles that are far apart most likely don't interact, you can leave out these edges in your graph and have, for example, a k-nearest neighbor graph on which you apply the message passing. You know, the graph neural network in this case would predict the latent interaction graph. And now it doesn't have explicit supervision for this. So it would essentially predict a posterior distribution over which edges or which pairs of nodes it believes are interacting in the system. And we formalize this by essentially saying we assume a discrete posterior distribution. And in this case, we use the Gumbel softmax trick to kind of soften this discrete distribution so that we can train it end to end with gradient descent. And the way we train the model is we, again, starting from this latent interaction graph proposal that the model proposes, we decode back into the original observation space. again using a graph neural network, but this time this graph neural network is only allowed to pass messages along the edges that the encoder graph neural network has predicted. And so in that way, the graph neural network, for example, cannot make use of any information about the state of a neighboring node to which the encoder has not predicted a link. And if we now impose some kind of sparsity prior, for example, on this relation, on this latent graph, the model has to be very careful in choosing the most essential edges which it can still use in order to still be able to either reconstruct the dynamics or predict the future dynamics of the system. And we can achieve this by either by essentially applying a simple reconstruction loss, in this case just a log likelihood, the expected log likelihood of the system using the standard variation autoencoder formulation, but also applying a regularization term where we try to ensure that the predicted posterior is close to the prior that we predefine a priori. And in this prior, we can include, for example, assumptions about the sparsity of the graph. Like, for example, we could say we want a graph that is as sparse as possible, or we want a graph that is relatively dense, for example. And this simple recipe suffices for, on the one hand, accurate modeling of physical dynamics of these simple systems that we looked at here. So here we have systems composed of multiple particles in some kind of toy box environment where they can swirl around in 2D and they're interacting based on some hidden forces between them. For example, in the left image here, they're interacting based on Hooke's law, like spring forces. In the middle representation here, these are particles that interact based on Coulomb forces, like they're charged particles, either positively or negatively charged. And then this Kuramoto model on the right, we have individual oscillators that interact using a nonlinear interaction force. And so in all of these systems, the interactions are quite, so the forces or the edge update functions the model has to learn are quite diverse. And still the model can accurately learn to infer both the latent edges, like the latent interaction graph in these cases, but it can also predict the dynamics forward in time relatively accurately. And so what we find is that in these systems where we do not provide supervision on these latent interaction graphs, this NRI model here in the learned setup where we learn the entire model end to end is close to what a supervised model could achieve on these data sets, where we would have privileged information about these latent interaction graphs. And what's interesting is that this model is not only useful for discovering certain interaction types, like if one particle is connected to another particle by an attractive or repulsive force, but it can also be used as a framework for amortized causal discoveries, as shown in this paper here by Cindy Lewin, David Matras, and others. And this is effectively because the model, if you make certain assumptions that no messages can be passed along, or that only messages can be passed along edges that the model has predicted, then effectively that means that in a so-called nonlinear Granger causality sense, that the edges the model will discover are the ones that are necessary for causal influence of one node to another node in the system. And on the other hand, this system is also not limited to inferring any kind of unstructured graph, but you can also make certain assumptions about the structure of the graphs you would like to infer. For example, as shown in this paper by Paulus and Joy and others, you can combine neural relational inference with so-called stochastic softmax tricks. And that allows you to limit the graphs you discover to, for example, latent spanning trees in this case. And then the model becomes a relatively accurate model for essentially inferring latent spanning trees only given observations on the nodes in the system. And this whole topic essentially sits in this field of latent graph learning. And latent graph learning has been around for quite some time before deep learning. For example, there has been work, a range of works in the the community of dynamical systems modeling, using either linear models or models with well-defined basis functions, where you try to fit certain interaction functions to the interactions in your system. By that, you can also infer interaction graphs. And it has also been addressed by the signal representation learning community. And similarly, it's also an emergent area for graph neural networks now, as for example outlined in this blog post by Michael Bronstein on latent graph neural networks, or in a range of recent works that try to include modules like these in larger scale graph classification benchmarks, for example, or node classification benchmarks, where you would try to jointly infer the graph over which the messages are passed and solve some kind of downstream task, which is other from simple reconstruction like in the example before. But also if you think about it, then attention mechanisms and transformers in general address a very similar problem. Effectively, the inductive bias they make use of is that the model has to infer a latent, like a sparse interaction graph among which it can pass messages. Also in the NLP community, there have been works, for example, that try to put certain priors on these graphs that are discovered so that you can transfer them from one task to another and get certain generalization benefits out of it. But any kind of sparse attention mechanism these days can be viewed under this lens of latent graph learning. So this concludes the part of my talk about relation discovery. And I want to spend a few more minutes talking about entity discovery in the context of this work on slot attention that we had at NeurIPS last year. And so the problem of entity discovery is essentially to learn a mechanism that abstracts away from some kind of perceptual data, like in this case, an image, into a set of representations that each of those representations should then capture, for example, an object or the background in the image or parts of objects. And in this work, which was joint work at Google Research with Francesco Locatello and others from the Google Brain team, we essentially frame this as an image to slot inference problem where we use an iterative competitive attention mechanism on top of some kind of encoder, for example, a convolutional network applied in images. And we can train this model both in an unsupervised fashion by essentially training it to reconstruct the input by letting the model go through this bottleneck where it has to abstract away the input into a set of latent variables that act in the same way as nodes in a graph, essentially. But we can also train this model in a supervised way by essentially letting it predict a set of these nodes and then using a matching loss to compare these to certain ground truth target descriptions of objects, for example, object color or object positions. And the core prediction problem in this case is to learn a mapping from an image or some kind of other modality to a set of variables. And this also means that intuitively, each element in this predicted set that we also refer to as slots should capture an object, part of an object or the background. And this overall problem is quite similar to capsule networks, with the main difference that here slots are symmetric or exchangeable under permutation symmetry, essentially. So this means that the ordering of the slots that we predict doesn't have any particular meaning. And this is the same kind of assumption we make in graph neural networks. Whereas in capsule networks, you would assume, for example, that the first capsule is like a tree capsule that captures mostly features of trees. Then the second capsule might be a house capsule that captures mostly features of houses and so forth. So capsules in capsule networks are class specific or type specific, whereas here slots are completely symmetric under permutation. And then that also means that each slot can capture basically any kind of feature in the input. And if you look at just how this model is implemented, you'll see some nice similarities to clustering mechanisms or grouping mechanisms in general. So what the model does is at the first we start by initializing the slots that we would like to infer from the image representation. just using a normal distribution. So we just initialize them at random, and then we perform a number of iterative updates. And during each iterative update, essentially, we compute a dot product attention mechanism score. So essentially, we have the input features from the CNN that we augment with position embeddings, and we have the output slot representations, which are still random at this stage. And then at each time step, we compute an inner product to compare essentially the current inputs with the output slots, and we score them based on pairwise similarity. And lastly, we pass these scores through a softmax, just like in a regular attention mechanism, with the main difference here being that we normalize the softmax over the output slots, so over the output of the attention mechanism as opposed to the input. And this ensures that essentially slots have to compete against each other for explaining locations of pixels in the input. And we aggregate these updates that we computed. So we aggregate the inputs that we aggregate the inputs using the weights we computed, using a weighted mean to get the updates, which we then feed into a recurrent module, like a gated recurrent unit in this case, to update, to compute the new slot representation. Now, the interesting part is when we start comparing this to a classical clustering algorithm like k-means or soft k-means in this case. And if you write down soft k-means in the same way as you write down slot attention, you'll see that effectively what slot attention is doing is a learned version of a kind of a parameterized learnable version of soft k-means. So instead of in soft k-means, instead of having a query and a value transformation, a key query and value transformations, which are these q, k, and v functions on the left, which are linear projections that are learned as part of the model. In soft k-means, you would simply directly compute the scores in the representation space of the input. And lastly, you would also not have a recurrent update function, but you would simply override the updates from the k-means update into your slots, which are the cluster centers. And looking at the similarity between these two algorithms, we see that essentially in slot attention, slots have to compete for explaining parts of the input, because essentially what they do is they perform a clustering of the input. And that means no two slots can explain the same input, or they have to compete for explaining the same input. And we can train this model now in an unsupervised architecture by, as I mentioned before, simply auto-encoding the input. We start by passing the input image through a CNN, use the slot attention module on top, and then decode each slot individually using a CNN decoder. And we recombine these the final slots into a composite image using a decoder that we take from, or that is inspired by this work, Iodine. And there are many related methods that address this problem, like Tagger, Square, Monet, and others that essentially address this kind of unsupervised discovery of object problem. What's different in slot attention is that it uses an iterative attention mechanism to essentially amortize this problem into a simple single learnable module. And essentially what we find is that this model can learn object representations from individual scenes, like these simple clever scenes here on the left, where you have multiple objects on a gray background. And the model can learn to decompose the scene into individual objects, and then we can reconstruct each slot individually and inspect the learned representation. And what you see is essentially that each slot captures exactly one object in the input, or it captures the background. And the background is kind of smeared over different objects or different slots because it doesn't have a certain symmetry behind it. So there's no particular preference for the model to capture the background in a single slot or to spread it out over the entire representation. What we also find is that if you now run this attention mechanism for multiple time steps instead of just the number of time steps that we use during training, let's say we use 3 time steps during training, then we find that if we run this grouping or clustering mechanisms for more time steps at test time, then results keep on improving. And this tells us essentially that the model has learned like a general abstraction mechanism away from, or general clustering mechanism away from low-level visual features into high-level object representations. And this algorithm also extends to more iterations of test time. And we also find that we can run this, for example, on scenes of 6 objects at training time, but it generalizes to more objects at test times, like 10 objects at test time in this case. And this finding essentially is possible because the model uses a set of symmetric output slots. So it's essentially set prediction model, and we can change the size of the set at any time. So we can let it infer 5 objects for one scene or 10 objects for another scene and so forth. And if you visualize the individual attention masks or the reconstruction components of the model, we find that essentially in the beginning of the clustering, these are still very inaccurate, and the model mixes up multiple objects in a single slot, but then over a number of iterations, this quickly improves, and the model is able to decompose the scene into individual components. And here's just one more example of what we find if we apply the scene, if we train this model, for example, with 11 slots on a scene with maximum of 6 objects, and then at test time, we apply it to scenes with a maximum number of 10 objects. And in this case here, the model learned to put the background into a completely separate slot, so it looks a bit nicer in terms of interpretability. And it also learns to keep objects, to keep slots entirely empty if it doesn't need them. So a couple of open problems in this field are essentially that these types of models, they tend to only work on very simplistic scenes with simple textures like the ones you've seen before. And one big challenge is essentially to make them work on scenes of highly complicated textures. And one solution, as proposed in this paper here, step-supervised video object segmentation by motion grouping, is to, instead of clustering pixel representation, we cluster optical flow, which essentially encodes in which direction each pixel moves at every time step. And this essentially gets rid of textures, and so you can even apply this to real-world videos. And similarly, an interesting extension is this paper, Right for the Right Concept, where the authors essentially show that you can interface with this type of model by using symbolic annotations. For example, you can have a symbolic annotation that says, ignore the color when making a decision. And then because the representation that the model learns is almost symbolic itself and easily interpretable, the model can, you can very easily interface with these representations and tell the model to ignore certain components of the input when making a decision. Now, before I conclude, I briefly want to mention how this can all be fit together in like a line of work that is often called a structured world model, or slot-based object-centric models. And the main idea behind this line of work is to start from some kind of low-level representation, like an image or an audio wave in this case. And you would like to abstract away from these low-level representations into a high-level abstract slot representation, where each slot essentially corresponds to one node in your input. And then you can use like the standard graph neural network toolbox on top to perform any kind of reasoning, dynamics modeling, or comparison once you have these representations. And you can directly optimize this for some kind of downstream task or loss. This could be dynamics prediction, but it could also be some kind of reasoning task. And the core observation here again is that everything that happens after the abstraction away from the visual features, or from the low-level features, is symmetric under permutation, and that essentially allows us to apply the graph neural network toolbox to these kinds of problems. And one line of work I want to highlight here is this paper on contrastive learning of structured world models that we had at ICLR last year, where essentially we take some kind of observation from an environment, which is in this case an image. We extract objects using a CNN, encode them using an MLP, and then once we have these object representations, we can reason on top of those using a graph neural network that predicts what happens next to the system under an action. And we can train all of this using a contrastive loss, which avoids reconstructing everything back into pixel space. And I won't go much into details here, but the high-level idea is essentially to use a very simple mechanism for object extraction. So this was before the slot attention work. So what we did here is simply say each feature map in a CNN is one object, and we encode it using an MLP. And this works for very simple environments where you have very clear object colors and very unique colors. But this would fail, for example, if you had multiple objects of the same color or same type in the environment. And once we have this abstraction and these abstract object representations, we can simply use a graph neural network on top that acts as a transition model. And this graph neural network has a message update function, like an edge update function and a node update function. And it also takes input the current action that, for example, an agent applies in the environment. And it predicts the updated node representations that happen after the action is applied. And altogether, one could train this, for example, with an autoencoding loss like in slot attention, but we found that especially for things like Atari, where you have highly textured environments, it's easier to train these models with a contrastive loss, where you score tuples based on your experience buffer that an agent collects in these environments. And you contrast it against some random state pairs to make sure that the model puts things that are close together in time, close to each other in latent space, and things that are far apart from each other, far away in latent space. And we tested this in a number of environments, things like simple environments. We have shapes that you move around with an action, or simple Atari environments like Atari Pong or Space Invaders. But one can also apply this to environments where you don't even have any actions. And in this case, you would simply apply the graph neural network to model the dynamics of the system for the next time step without any action. What we find here is essentially that despite us using only such a simple object extraction mechanism, this model can still learn object-specific feature maps that correspond to particular objects in the scene. And it can also learn interpretable object representations and transitions. So what this shows here is essentially the latent space in the left case of the yellow object in the scene. And we find that under each transition, like if you apply an action and you want to move the yellow object in a particular direction, then the edges in this latent space transition graph here show what the model predicts what would happen after applying this action. And so the model, if you keep all the other blocks fixed and only move the yellow object, the model correctly kind of maps out the entire latent space, and it knows that it cannot move the object where other objects are currently placed because of the graph neural network interaction model. And so this is kind of a nice indication that we can, in fact, learn a model end-to-end from pixel space that abstracts away into objects, and then use things like graph neural network on top to generalize well and to learn interpretable representations. And so to conclude, I essentially talked about relation discovery, where the graph inductive bias or the GNN inductive bias is not only useful for learning with graph structure data, but also for discovering relational structure in graphs. And lastly, entity and object discovery is still a major open problem in machine learning, essentially how to find symbol-like and composable abstraction in an automated manner. And these kinds of differentiable attention-based interfaces that I mentioned earlier are a promising direction for exploring this further. So in terms of next steps, I think applying structure discovery methods to other domains like text, speech, or video, but also exploring other learning paradigms beyond, say, autoencoding or contrastive learning by, for example, looking into reinforcement learning, are promising avenues for future work. And this also leads me to the point about combining structure discovery and reasoning or prediction in kind of a single framework. So you learn the optimal graph structure, both in terms of entities and relations for a downstream task, instead of the user of the system having to provide the optimal structure in advance. And lastly, we also need more benchmarks in this area, which are crucial for measuring progress. And with this, I'd like to conclude, and I'd like to acknowledge my collaborators, both at Google Research and at the University of Amsterdam, where a lot of the earlier work I mentioned in this talk has been carried out. And I think we have some time for questions and discussions. Thank you.
Thank you, Thomas. So yeah, please, if members of the audience, if you could add your questions to the QA. I can see that we've got a few coming in now, so keep adding more questions to QA. I'm going to hand over to Johannes in a second to conduct the QA, and then me and Alessio will just kind of run things in the Zoom. I actually have one question, just to get the ball rolling, Johannes, if that's okay with you. So Thomas, first slot attention, how sensitive is it to, you kind of touched on this, but quantitatively, how sensitive is it to the number of slots? And could you, for instance, could you accurately predict the number of objects? Could you count the number of objects?
That's a really great question. And essentially what we found is that there is some slack in terms of using too many slots. Like, let's say there are scenes with up to 6 objects. You can use up to, say, 10 or even 15 slots without affecting the performance negatively. But if you would use too few slots for the model, then the model would not be able to decompose the scene accurately. And essentially what we also find is if you provide way too many slots, then it can happen that the system finds a better solution where it decomposes individual aspects of objects into different slots, which in this case just provides a better solution for the clustering problem. So if it has too much capacity, it could, for example, split certain parts of a cube into a separate slot and keep other parts into a separate slot altogether.
So does that mean that you wouldn't be able to accurately count the number of objects in a view?
So in this case, in these examples that you've seen earlier, where we use a roughly accurate number of maximum slots. So these were scenes that were trained with 3 to maybe 10 objects, and then if you use something like 10 to maybe 15 slots, then the model could accurately predict the number of slots because that information is encoded. But it is not completely insensitive to this hyperparameter.
Okay, thanks. Over to you, Johannes.
Thank you, and thank you, Thomas, for the very nice talk. I think one very interesting direction that I would discuss a little with you is this complete end-to-end question of like how, if you only have an image, like how can you first get the entities out of that, then a meaningful relation, and then ideally even do reasoning on top of that.
Mm-hmm.
So I've seen, and you talked about work that does every one of those steps. So you talked about entity extraction and relationships. And there's also been, especially with scene graphs, so if you have an image, you can then annotate the image as different objects and then have relationships, which are usually more complex. So you don't just say, hey, this has a relationship, but rather you say, this is under this, or this is composed of that, etc. Have you seen work in that kind of uses this whole pipeline and goes from end to end successfully?
So far, I haven't seen work that has attempted the whole trajectory end to end, and I think this is still kind of a major open problem, how to find the right trade-offs. For example, if you want to do object discovery end to end on video, completely unsupervised, then so this is easy to do on things like these clever-like environments. We have very simple backgrounds and colorful objects, and there have been quite a few works now that do this end-to-end, and they can also learn the dynamics on top. But if you want to do this end-to-end on real data, like just random videos with complicated textures, camera movement, deformable kind of physics, and all the complications of the real world, then so far this is still quite elusive. Yeah.
But at least you had some initial results in your CSVM paper, where you at least did Atari games, and you did the entity extraction, you did the relationship, and you had some success there, right?
Yeah, exactly. It depends on how you define success. I think this method is, thanks to the contrastive loss, fairly good at modeling, like first of all, learning representations of a scene. but also modeling the dynamics. But if you inspect the learned representations for Atari, then they often don't correspond to kind of the crisp objects as you would expect, but it learns some kind of some very difficult to interpret features. And I think the question is always like, what do we want to get out of it in terms of interpretability? I think many of us think like, okay, if you train these end-to-end in the right way and you regularize them the right way and you just train really large scale, what should emerge in the end is something like an intuitive object understanding like we have it as humans. And that's kind of like the big goal that many are following on. The question is like, is this enough or are we missing something more fundamental? Like, do we need particular additional requirements beyond like the symmetry, which seems to be a core requirement, like the permutation symmetry of objects?
Right. I just remembered in your C3 paper, even in one of the Atari games, I think it was Pong, you've even found that just using a single slot worked best, which essentially means that you lose the whole structure, right?
Yeah, so Atari Pong is quite interesting because effectively the opponent agent and where the ball is very much correlates with your own actions. And so it seems like you can without really having to make use of permutation symmetry, describe the scene basically just using a single slot. Also, in the end, if there's just 3 objects in the scene, like the ball, the opponent pedal, and your own pedal, and the opponent pedal and the ball are basically always in the same kind of the same height, then this is not very difficult for the model to essentially just encode into a single vector representation and make use of that way. It might actually be harder for the model, it seems, to properly like learn a per object representation and make use of that.
Which would be the actual goal, right?
Yeah, exactly. So there seem to be just many shortcuts that these models can learn. And I think we will only find out if we find a way to scale these models to truly large scale. So that shortcuts are just not possible anymore. And yeah, that's still a major open problem. Like, I mean, on simulated data, I'm pretty sure one can scale these models already as they are right now, if it's like very simple, clean data, like Clever. But as soon as you want to go to something more interesting and more complicated, it gets really tricky.
Right. I guess this also is related to things like AlphaStar and OpenAI, which essentially they didn't use the video, but instead they hacked into the game and actually got the objects and the relationships from the game directly, and therefore skip the whole entity extraction part.
Exactly. And at this stage, we don't, I believe, to the best of my knowledge, we don't have any method that can learn like to do well in any kind of complicated game that is really multi-entity, that cannot be well described by simply a grid of abstractions, like a game like Go or chess. You can simply use the grid, and the grid is almost a perfect abstraction already. But for many video games, you don't have this luxury, and especially in things like StarCraft, I guess you would want to have an entity abstraction, and this has also been the case, exactly like I mentioned, for these works that carefully handcraft these entity abstractions.
Okay, nice. Moving away a little bit from reinforcement learning, we had one person ask if there's been results in a similar manner in NLP, where you take the text, you get entities from the text, and then really do reasoning on top of these objects.
That's a really good question, and this is starting to become an emergent popular direction in NLP, and I recommend looking at the work of William Hamilton. So he with students had some interesting results on a benchmark called Text World, where essentially you have to reason about like a dynamical system where you can make actions, but everything is represented just by text. And so you would have to represent the environment using entities and their relations that you extract from text, and then the transition dynamics by taking actions in this environment. And it turns out that graphs are like, if you learn this kind of graph representation in these kinds of environments, this also gives you a generalization benefit, as opposed to trying to kind of just do everything end to end with a simple transformer on the text directly.
And that's completely learning the entities. I mean, right? Because a simple approach for using graphs on text would be just to take the grammar and build up trees based on the grammar, which people also have done.
Exactly. So there has been, also for summarization, have been interesting works that basically try to abstract away from the textual data by linking entities across documents, extracting entities in the first place, and then using those as the graph representation, among which on top of which you then apply graph neural networks. And this also gives you generalization capabilities. But then usually you would make use of privileged information that you have as a human, knowing that these are entities, these are certain grammatical relationships and so forth.
Right. The groundedness in reality, the famous. Okay, we have again a bit of a different question here that's related to your earlier work regarding applying GNNs to physical systems, which essentially have a dynamic graph and then use this to predict the next state of the physical system. So the question is, would this be possible? And I mean, and how would you approach this?
Essentially, how to use graph neural networks to predict the next state of a dynamic system, if I understood the question correctly.
Yes.
Yeah, so this is something that, well, also you have worked on, Johannes, but also others in the community. And essentially, the answer is these models start to become really good at essentially learning to imitate simulators, where the simulator would be like a kind of ground truth description of the physical system. You roll them out, and then you can train a graph neural network, which essentially the update functions in a graph neural network look very similar to certain functions in certain physical simulators. Like you have messages are the forces that are exchanged, and the node update functions are essentially how you aggregate these forces and update the acceleration or the speed update of the particle or position update. And of course, the challenges here are usually, if you look at physical systems, is how do you make use of all the symmetries in a physical system? Your system might be symmetric under rotation. Like you don't want to care about if your system is in a certain rotation in your coordinate system, but you would like to make use of the symmetry in your model. And there have been really exciting works in this space as well, like Johannes' work.
Yeah, let me maybe add something onto that. The easiest way to do this wouldn't even involve having the GNN predict further states in the future, but rather just integrate it with a normal simulation. So you just have the GNN predict forces or accelerations, and then you do a time step based on these, and you get a new state, and then you again do a GNN, and this predicts the new accelerations, etc. And then you just do this for a long time, and that can be very accurate. A different question regards the scaling of GNNs, especially how do they scale during training? Do larger graphs need more message passing steps to be accurate? And whether we can overcome this if we learn a high-level representation of the graph's relations.
Oh, that's a very interesting question, especially the last part. I think in terms of, I'm going to start by addressing the number of message passing steps question. So that is very much data dependent. And I think a good estimate for that is usually the diameter of a graph, like how far, what is the maximum distance between any two nodes. At least that gives you, if you want to be sure that every node knows about every other node in the system, which you might not always want to have, but if you want to make sure if this is important for your problem, then you want to have at least as many message passing steps as the diameter of the graph. And for social networks, this can be fairly small, like 7 or so. But typically, people find a benefit of using deeper graph neural networks these days with multiple message passing steps. Of course, this becomes very expensive if you apply this on large graphs. And so in terms of scalability, I think the big challenges are essentially how do you make use of distributed compute centers with multiple GPUs or TPUs, and how do you actually efficiently implement these models? Or how do you approximate kind of the graph structure so that you might not have to pass messages over every single edge in the graph? And the last part you mentioned, the question what the question was about is like the question of how can we make use of like maybe learned skip connections or even learned like high-level abstractions, like you might want to abstract away from a whole cluster of nodes because it's way too expensive to perform message passing between like each individual node all the time. And I think this is still in like early stages exploration in this direction. I think there's lots of interesting stuff to be worked on.
Yeah, regarding the high level question, I've seen a paper that was like iClear 2020, I think, called Graph Zoom, where they were quite successful with, I think they used graph clustering, and they had the low level where they used a full graph, and then they had multiple higher levels. The question there was unsupervised node embedding. So they essentially created embeddings on the highest level first, and then they fine-tuned them on the low levels, etc. And this also made the whole problem extremely scalable. So there are a lot of tricks you can do with this multi-scale approach. Definitely.
Yeah, I fully agree.
Guys, I think we should call things to a close. We're slightly over time. Thanks so much, Johannes, for conducting the QA and for the really interesting discussion points. And thank you so much, Thomas, for a fantastic talk. Really, really wonderful talk again. And hopefully we'll have you back again in a couple of years for another talk. And thanks to the audience for coming along. Really appreciate it. If you haven't seen the YouTube channel, then the talk's going to be recorded. All of our talks are recorded and they're on the YouTube channel. If you're watching on YouTube, then click subscribe, and then you're going to get to find out about future talks. Thanks again, everyone. See you next time. Bye-bye.
All right. Thank you, Martin. Thank you, Hannes.
Thank you.